Hello and welcome to session number 12. We're still talking about the soils and soil analysis and all of that, but when things come into the picture, I have to stop for a moment and perhaps change course a little bit. Today we're going to be talking the organic matter content of soils. And you would remember from that pie chart that nearly on average 5% of the soil volume is organic matter, but this figure is flexible. It goes up and down, with the location and the amount of organic matter production and all of that. But even if we look at, let's say, 1% of the soil weight, assuming it's all organic matter, when you have removed all the moisture from the soil, because it doesn't really count. So 1% of the soil weight per hectare is 20 ton. Remember that. It's a daunting figure, especially if you want to consider fresh organic matter that's got a lot of moisture in it. So if you want to increase your organic matter content by 1%, you need a huge amount. And it's easier said than done. And a lot of people think that they can easily, just by doing some composting, of their rubbish and a bit of refuse here and there, and they throw it around the plants, that they can effectively increase the organic matter content. It won't. It will help a lot, perhaps with the cation exchange, okay, and I'll explain the difference, but to lift the organic matter level is very, very difficult. And every area realistically has its ceiling of how much organic matter it can have. And this ceiling is stipulated by two main things: the rainfall, the average rainfall, and the ambient temperature. Because if you have, let's say, of course, the higher the rainfall, the more organic matter is produced. The higher temperature, the more organic matter is produced. But also the higher will be the rate of breakdown. So the organic matter is always in a constant case of flux. Some is produced, some is getting decayed. And if you make an input, for the input to be significant, it has to be huge in terms of weight, which is not always all that feasible. Okay, enough of that. Let's go back here a little bit and go back about this mineral fraction of the soil that has a negatively charged surface, which attracts components that are positively charged. Now, as we said, all of these here, all these yellow circles representing the minerals, they carry the mineral in a form that is available to the plant. However, those here swimming in blue are, number one, not protected against leaching. And number two, because they are in the soil, they are contributing to the salinity. So even though they're beneficial, but they are nonetheless salts, and they contribute to the salinity. Now, when you have a good organic matter content in the soil, this organic matter will latch on to these, or at least some of them. So it will increase. That's one of the benefits. I can't talk really about all the benefits of organic matter, otherwise I'll be here for hours talking about it. We all know that it's good for you and we need to encourage it as much as we can. I'm just talking about it in terms of increasing the availability of essential elements. So adding organic matter to this will grab these things and make them available and remove them from the solution, and thereby reduce the soil salinity. Now, this process here of electrostatic attraction, to bring it to mind, to make it something simple, easy to understand, just allow me to rub this plastic pen here to my pants as I speak. Why am I doing this? Because I want to charge it up. I want it to have some electrostatic features. Okay, so I've rubbed it enough, I think, and then I bring it close to those little pieces of tissue paper, and it will attract them. This is electrostatic attraction. This is exactly what happens here. So what happens when I rub it? This polymer here will lose some of those electrons on its surface. They will just drop off, leaving behind a positive charge, and then they will attract themselves to anything that can give them these electrons. They're just hungry for electrons. So that's the process of cation exchange. Okay? All right. The reason I'm emphasizing this is because I want to draw the distinction between this process and the process of chelation. you would have heard the word chelate, I am sure. A chelate, the word comes from Greek, comes from the origin claw, you know, like a cat's claw. There are two types of chelates. There are the natural ones, of which organic matter are a big example. Okay, perhaps they are the biggest example, but chemically speaking, they are complex. They're very difficult to understand, really. The synthetic ones are much easier to understand because they are like well-defined chemicals. We know exactly what they are. One of them, the most common one, is EDTA. EDTA is ethylene. Okay, that's all right. Sorry, I had it upside down. Forgive me. EDTA is ethylene diamine tetraacetic acid. Now, never mind the long name. The reason I mentioned it is because I want to emphasize this tetra. Tetra is 4. Tetraacetic acid. All of these things, 1, 2, 3, 4. There are 4 arms of acetic acid, each with a negative charge on it. Okay? So what do you think happens when you approach this rather strange-looking, funny, spider-looking molecule? When you approach it with a positively charged particle, let's say a sodium ion. Sodium ion means a sodium atom that has lost an electron, so it is now positively charged. Those negatively charged arms will immediately latch themselves to it and grab it. Grab it. Because positive attracts negative, just like we had here with this electrostatically charged pen. Okay? So this is the process of chelation. That's what chelation is about. But if you look at the scale, because that's very important, the scale is extremely important. Why am I emphasizing this? Because a lot of information, or misinformation, I should say, is being spread and spoken about in terms of chelation. Now, the size of this molecule, which looks rather large, I really haven't looked it up, to be quite honest. But it would be probably something in the space of end to end, I don't know, maybe 20 nanometers, maybe more, maybe less, but it wouldn't be much more. In fact, molecules are not measured, or atoms, their size is not measured by nanometers, it's measured by angstroms. And an angstrom is 1/10 of a nanometer. So when we talk about nanometers, we're talking, nanoparticles, we're normally talking about things that are measured in nanometers. And a nanoparticle, you know, you don't really start calling it a nanoparticle before it's about 100 nanometer in size. Up to 500, maybe 1,000, I don't know. This is a flexible definition. But this definitely is not a nanoparticle. It's a molecule. And what it grabs, those single things, these are definitely way, way smaller in size than what you would refer to as a nanometer. Because, as nanoparticles, sorry. Because the size of these things would be 1 or 2 angstroms, which is 0.1 or 0.2 of nanometers. So those chelating agents, whether they are synthetic like this one or natural like the other ones that we are going to be talking about, all right, they can only actually grab very, very small particles. And talks have been said and spread about some agents which are not really chelating agents to begin with, okay? They are minerals. They are minerals that have the ability, I keep holding this upside down, I'm sorry. There are minerals that are able to do this cation exchange. So they're being described as being chelating agents, which they are not, number one, and that we are told that they are able to chelate nanoparticles. Wrong, 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 wrong. Chelating agents are only able to grab tiny ions. Okay, so that's so much with this bloke here, which is a synthetic one, but very useful tool to understand the process of chelation. Now, the natural chelating agents, like the ones that we find in humus, are something like this. And this is, again, a very small portion of it. It would be much, much bigger than this, with many branches and other particles going in it, and sometimes well-defined chemical formulations, sometimes not so much so. But the bottom line here is that they also have negative charges, which in this example here is attracting sodium, but equally it can attract potassium, magnesium, calcium, any of these things. So organic matter, when it's in its final form, we say humus. Take your organic matter and compost it. Why do you want to compost it? Because fresh organic matter is comprised of huge organic molecules that don't have these properties. They have the potential to have these properties only after they break down. Just like when we eat food, we have to digest it. There's a gradual process which starts with chewing and then gastric juices, intestinal juices, etc., until it's broken down to its components. Organic matter is also broken down by soil bacteria, mainly, until it ends up in the form of a humus, which is the effective substance in compost. Now, of course, not all of compost is a humus. A lot of it is still organic matter that is still under decay. But when it reaches the stage of a humus, it reaches the stage beyond which further breakdown becomes virtually impossible. Like if you take organic matter and burn it, when you burn wood, it turns into ash. All of these things are broken, you destroy everything. Humus is not so much such a stage of degradation like ash, because with ash you have a burning process which destroys everything, and all it leaves behind is just the minerals and the inorganic fraction. And we'll be talking about burning next time, because this is the process that we're going to be using in order to be able to measure the amount of organic matter in our soil. I think I have said enough today about this subject. And if you have questions, please do so on the blog, ask the questions, and on the Facebook page, on the like page, I'm more than happy to answer them. That's all for today. Thank you for listening. Bye-bye.